All right, we are back. Let's talk about amide chemistry. So the reaction we're going to look at is conversion of amides back to carboxylic acids. And although going from a carboxylic acid to an amide is rather difficult, going from an amide to carboxylic acid is not as complicated. And it has to do mostly from the fact that, water is not as basic as amines are. And so you don't really run into this problem of having to like moderate the pH and make sure that the conditions are just right for the reaction to happen. You basically add acids to your reaction, and you have plenty of water around. And aside from that, you just have to have a little bit of heating going on. You probably have to reflux this reaction to like really get it to go all the way to completion. But what will happen is that you will protonate the carbonyl oxygen, kicking away the electrons back to the oxygen of your hydronium, which now will be turned into water. And once this is activated upon that protonation, a water molecule, which should be the solvent in this reaction, will attack the carbonyl carbon, kick away the electrons back to the oxygen, and form this intermediate. So just like we saw in the previous examples, we're going to have a proton shuffle take place, right? So another water molecule can come in, attack the protons of the oxonium cation, kick the electrons back to that oxonium oxygen, and in the process form this neutral intermediate. Now the hydronium that has been generated will come around and it will dump the proton on the nitrogen of basically the amine component of this molecule, right? In the process, you will reform water, but now you have a good leaving group, an amine leaving group this time around. So the oxygens of that hydroxyl will have its electrons come back down to reform a double bond. And in the process, you will kick out your amine derivative. And like the big difference right here compared to the process of going from carboxylic acid to amide is that you don't have a bunch of amine in solution. So it doesn't matter, right? How much acid you're using, how low the pKa, or not the pKa, but the pH of that solution is. In essence, the lower the pH, the better, because this amine that's being formed can then react with the excess acid that you have in there and completely be taken out of the equation entirely, right? And case in point, right? That amine can easily serve as the proton sponge, which will remove this proton from your carboxylic acid. And in the process, right, you form your carboxylic acid. Now you have an ammonium salt that's kind of like stuck in that position, right? Especially if the pH is low enough to push the equilibrium of the ammonium to remain in that state. So this actually happens really well. So you can make carboxylic acids relatively easily from amides, which is not the same as going from carboxylic acid to amides, right? Amides to carboxylic acids, good. Carboxylic acids to amides, not so good. All right, but with that said, there's one reaction that we haven't quite talked about. And the reason why is because it involves nitrogen. And it is basically the formation of nitriles, right? We haven't really talked about any of them because all of the other reagents contain oxygen, right? So they didn't really do the trick for this. So there is one way to actually make a nitrile, which is kind of interesting. Pretty much, it's the one reaction that's kind of beneficial for you to start with an amide. So you can make the amide and turn it into a nitrile ultimately, right? And the way you do this is by treatment of the amide with thionyl chloride. And, in this case, remember that the amine is, pretty much donating its electron density to the carbonyl carbon. So the carbonyl carbon can pretty much be broken to attack the thionyl chloride over here. And in the process, you form this intermediate, right? But now you have this iminium intermediate. You have broken that carbon-oxygen double bond in the process, right? But now you have an elimination at the sulfoxide, right? Because you reform, I should say, the sulfur-oxygen double bond, and you kick away one of the chlorides. All right, now what ends up happening right now is that the protonation takes place, but specifically, at your your nitrogen, right? So one of those protons on your nitrogen is removed. You could use the chloride for that purpose, right? And technically speaking, although yes, you could make the case that yeah, that proton is probably it's going to go to nitrogen exclusively. Eventually, what's going to happen is that whether you do that or not, that set of electrons is going to come down here to reform, or not really reform, but just form a triple bond altogether. And the only way for that to happen is if you kick out this group entirely, right? So kick this set of electrons back to sulfur, you will form a sulfur-oxygen double bond. And of course, you will be kicking away another Cl derivative. So this will ultimately produce sulfur dioxide, which once again is a gas. You'll have HCl that's also present in there. But then you have protonated nitrile, which will be deprotonated by Cl to form another equivalent of HCl in the process and produce nitrile. So this is a pretty cool method of making nitriles directly from amides altogether. So, one particular synthetic route will be to start with a carboxylic acid, turn it into an acyl chloride. You could turn that into an amide and eventually into a nitrile. And beforehand, the chemistry that we've talked about in previous chapters could very well apply. You could extend the carbon chain to whatever you want it before you do these transformations all the way to a nitrile. Okay. But in much the same way, we can also go backwards, right? We could start with the nitrile and we can force this to go to the amide stage. And in many ways, you could make the argument that this is nothing more than the opposite reaction, the inverse reaction, right? We start by first protonating the nitrile. And after that protonation, which leads to activation of the triple bonded carbon, we have water attacking that triple bonded carbon and kicking away the electrons to nitrogen, forming this initial intermediate, basically an imine intermediate. Now, here we will have a deprotonation event where the hydrogen of oxygen will be removed, right? So we could have water come in, attack that proton, have the electrons back to the oxonium oxygen, making a neutral intermediate right here. And what you end up doing is now shuffling that proton. Now the proton gets dumped onto the nitrogen. So nitrogen attacks the proton. Those electrons go back to oxygen. And now you have this iminium intermediate. So then the next thing that happens is that you basically have, and you could do this concurrently if you want to, right? So the protonation that basically kind of kickstarts this process of moving the electrons of that OH bond over to the adjacent carbon to form a new carbon-oxygen double bond. And at the same time, you'll kick the electrons back to nitrogen. And in that single step, you basically be forming your amide and, reforming your acid catalyst as well. Okay, so that's kind of how that goes. Now, technically speaking, if you do this under reflux conditions and kind of like rigorous conditions, technically speaking, you can take the nitrile all the way to the carboxylic acid stage simply because the nitrile that initially gets converted to amide can then be turned into carboxylic acid directly from the amide stage. So to show you that, right, let's start with the amide. The amide will be protonated by the acid. And then the protonated carbonyl, which is now activated, will then get attacked by water, right? So water will attack that carbonyl carbon, kicking the electrons back to oxygen, forming the following intermediate. And then the proton of that oxonium cation will be removed by another equivalent of water. The electrons will be kicked back to the oxygen, forming the neutral intermediate over here and reforming the acid catalyst. And of course, that set of protons that are on the acid catalyst are now being dumped somewhere else. Specifically, we're going to dump them on nitrogen, right? So nitrogen will get protonated, meaning the nitrogen attacks the proton, the electrons go back to the oxygen of the acid catalyst, and now we have formed a good leaving group, an amine leaving group. So the last thing is that one of the hydroxyl oxygen lone pairs is brought back down to reform a carbonyl carbon, and in the process we kick away the aminium or amine leaving group, to be technical, right? All right, last but not least, the protonation happens with that amine that you have formed. It basically attacks the proton over here. The electrons go back to oxygen. You have now formed your carboxylic acid and form an ammonium salt in the process. So this is definitely doable, right? And we showed earlier on that yes, this happens with amides. We can make this happen, go all the way to the carboxylic acid stage. So the fact that you can turn nitriles into amides also means that you can turn amides, excuse me, nitriles all the way to carboxylic acids. So yeah, something to keep in mind. And to give you a brief synopsis of everything, right? Because we've talked a lot about various kinds of reactivity. This matrix chart is meant to tell you roughly the reaction conditions that you want to do, right? So for instance, acyl chloride to acyl chloride is not really an option, right? But you can go from acyl chloride to anhydride. And the way you do that is by reacting the acyl chloride with sodium carboxylate. Or alternatively, if you want to make an ester from an acyl chloride, you do that by reacting the acyl chloride with either sodium alkoxide or alcohol in the presence of a tertiary amine like pyridine. You can make an amide by reacting acyl chloride with two equivalents of amine. You can make the nitrile technically from the acyl chloride if you first react it with two equivalents of amine and then you follow that up with thionyl chloride. The carboxylic acid can be either formed from the acyl chloride from sodium hydroxide, or if you react it with water with some base to remove the extra proton. So needless to say, the acyl chloride is the more versatile for the majority of these reactions, right? The anhydrides, you can make esters from anhydrides following these conditions. You could, if you push it, and if you're lucky, you can make amides directly from your anhydrides as well, right? Carboxylic acids can also be reformed from your anhydrides. And then your esters can serve the purpose of making other esters, or you can make amides, although that's the crap reaction I told you about. I would recommend you to avoid it at all costs. So for all intents and purposes, esters are good for making other esters, or esters are good for making carboxylic acids, right? That's kind of where it's at. And then the amides, really the only two reactions that are like feasible for it are the conversion of amides into nitriles using thionyl chloride, or the conversion of amides into carboxylic acids by reacting the amides with acids, water, and plenty of heating. All right, and then your nitrile, really the only two things that you're going to be able to do with nitrile is convert it to an amide using, acidic water, or take it all the way to carboxylic acid if you, heat it up enough. All right, the last thing, of course, is your carboxylic acids. You can make the acyl chloride from the carboxylic acid with thionyl chloride. You can make the anhydrides from the carboxylic acid if you first react the carboxylic acid with sodium hydroxide and you follow that up with the acyl chloride. You can make the esters from your carboxylic acid if you react the carboxylic acid with alcohol in the presence of a strong acid. And I would say the formation of an amide from the carboxylic acid is cute, but it's not a reaction that I would recommend you to do. It's probably going to be not very good in terms of yield. All right, one last thing, and this will finish up the entire lecture. So I just want to remind you that for some of these reagents, there are things that you can do that allow you to not only go from carbonyl compound to carbonyl compound, but you can actually now deal with oxidations and reductions. Now, specifically, this will be reductions because we're going to be going from 3 plus carbon to 2 plus carbon, or 1 plus carbon, or even like -1 carbon if we're going all the way to alcohols. So the acyl chlorides, you can make ketones out of them if you react them with cuprate salts. You can also make aldehydes if you react them with big aluminum hydride reagents. But you can also turn them straight into alcohols. With Grignard reagents, you can turn this into a tertiary alcohol. If you use a lithium cuprate to first turn it into a ketone and then you reduce the ketone, you can make a secondary alcohol. If you, on the other hand, simply react the acyl chloride with LAH, you can just make primary alcohols. And then if you turn the acyl chlorides into an amide by using amine, and you follow that up with SOCl2, thionyl chloride, you can make your your nitriles, which at that point you have to reduce with lithium aluminum hydride to your amines. So similarly, you can see that for the anhydrides, you have a similar process, right? Cuprates for ketones, big aluminum hydrides for aldehydes, Grignards for your tertiary alcohols, cuprates and reducing agents to get to the secondary and the primary alcohols. And then for the esters, you have a little less options, but there's still some options, right? You can use Debol to turn the ester into an aldehyde. You can use the aldehyde to turn an ester into tertiary alcohol. You could use aluminum hydride to turn the ester into a primary alcohol. The amides, the only thing you can do with reducing agents is to basically treat it with LAH to make amines out of it. And then your nitriles, if you react it with a Grignard and you follow that up with water workup, you can actually produce ketones from it. If you use sodium hydride and you follow with water, you could make your aldehydes. Direct treatment of your nitrile with LAH will give you the amine, as we discussed at the beginning, right? And then the carboxylic acids, as far as treating reducing agents, LAH is basically going to give you primary alcohols, but anything else is not quite an option. All right, so with this, I think you have the full scope of all the reactivity you can do. So this last slide basically gives you all of the connections in relation to reductions that you can apply to all these, more oxidized carbonyls, and hopefully gives you an idea of what you can do synthetically speaking as well. All right, so with that being said, I'll catch you in the next video, and have a good one. Bye-bye.